In this lecture video, we're going to start looking at applications of screening tests. The first application will be to random drug testing. Now, drug use by workers lowers productivity, decreases quality, increases costs, and increases risk for companies by decreasing performance of employees while on the job, increasing the number of sick days taken, and increasing the potential for accidents while on the job. Hence, it is in the best interest of a company to discourage drug use by its employees and to identify and appropriately deal with employees who do use drugs. Consider a company with a large trucking fleet. In order to discourage drug use by its drivers and to identify those who do use drugs, the company has contracted with a drug testing firm to implement random drug testing of its drivers. Now, this is clearly a situation of decision-making in the face of uncertainty. Let's consider such a decision-making situation. Now, first, how would you set up the hypotheses for such a test for a particular drug? So let's consider the possible null and alternative hypotheses that we could come up with. So one approach would be to use as a null hypothesis the employee does not use the drug. That would be our assumption when we select somebody for testing. Again, the assumption would be contained in the null hypothesis that the person does not use the drug. The alternative hypothesis would be the opposite of that the person does use the drug. Or we could set it up the other way around. We could assume going into it that a person that we select does use the drug, and then the alternative hypothesis would be that the employee does not use the drug. Now, with the first situation, we're assuming that the person does not use the drug, and we're allowing the data obtained through the test to convince us that they actually do use the drug. On the other hand, the second setup, the assumption is going into it that the person that we randomly select does use the drug, and we're going to let the data try to convince us that they do not. So how would you set up the hypotheses for such a testing situation? So a few questions here. Does it matter how the hypotheses are set up? If not, why not? And if so, why does it matter? And how does it matter? Now, consider those questions. We're going to set up the hypotheses in the first way that we discussed, where the null hypothesis is that the person does not use the drug, right? That's our assumption going into it. When we randomly select somebody to test, we're going to assume that they're not using the drug that we're testing for. And then the alternative will be that the person, the employee, does actually use the drug. And so we're assuming that they don't use the drug and then giving the data, giving the test the opportunity to convince us otherwise, to convince us that they do in fact use the drug. And so when we consider the two alternatives, the two ways of setting up the tests, and in particular when we consider the way that we are saying that we're going to set up the test, we need to think about what a type 1 error constitutes in each situation and what a type 2 error constitutes. And so using the setup that we're going to use, all right, where the null hypothesis is that the employee does not use the drug, the alternative being that the employee does use the drug, what is a type 1 error in that situation or with that setup, and what is a type 2 error in that situation or setup? Also, what are the relative losses or costs associated with these two types of inferential error, the type 1 and type 2 error? And which would you consider to be worse? Now, with the setup that we're going to be using, a type 1 error would be concluding that a person does use the drugs when in fact they don't. Now, the cost of that would be that the driver gets disciplined or perhaps even fired. A type 2 error, for the way that we are going to be setting up the test, would be concluding that a person does not use the drug when in fact they do. Now, what would be the cost associated with that? Well, one would be that a drug-using driver continues to drive, increasing the risk to the public and therefore to the company as well. Now, which type of inferential error would you consider to be worse and therefore to be more guarded against or protected from in this situation? All right, and so that is a subjective assessment. I can't tell you what the answer is or should be. You have to make that assessment. But now with that in mind, would you recommend using a smaller or larger level of significance alpha? And so this is getting at the balance that we have to think about when we are setting up a test, when we are deciding the significance level to use. You'll remember that alpha is the probability of a type 1 error, beta is the probability of a type 2 error. And you'll remember that the relationship between alpha and beta is that if we increase alpha, beta decreases. If we decrease alpha, then beta increases. And so this is why we need to identify what a type 1 error and a type 2 error represents in a given context. Then we also need to think about the costs associated with each of those types of inferential errors. And then finally, we need to weigh the costs of those two types of inferential errors in coming up with a reasonable significance level to use for the test. So in general, we would come up with a significance level to use, but what we're going to find out is that associated with the screening test is a corresponding significance level. So the screening test used by the drug screening firm has the following performance characteristics, and so we're just going to assume that this is the case. Let's assume that the drug screening or the screening test has a sensitivity of 0.95. Right? That is the conditional probability that the test comes back positive given that the person is a drug user. So in other words, if the person is using the drug, then the probability that the test detects that is 0.95. All right, so we've got a 95% chance of detecting when somebody is in fact a drug user. All right, that's a kind of a loose way to say that. All right. In addition, we're assuming here that the drug screening test has a specificity equal to 0.95 as well. In other words, the probability that the test comes back negative given that the person does not use the drug is 0.95. Now, these two values, the sensitivity and the specificity, seem fairly high, right? So the test seems fairly accurate. And I would also point out that while we're assuming here that the sensitivity and specificity are both 0.95, in general, these may not be equal. Let's put it that way. All right, there are going to be lots of situations where the sensitivity and specificity will be different, and in fact, that will probably be the norm. Right, that'll probably be the usual situation. But just for the sake of this example, we're going to consider a test where the sensitivity and specificity are both 0.95. And so, again, we have our hypotheses, all right, the null hypothesis being that the employee does not use the drug, all right, so that's our assumption about the employee going into this, right? We randomly select an employee and we're going to assume that they do not use the drug. We're going to give them the benefit of the doubt, and then we're going to let the data through the screening test try to convince us otherwise, all right? Now, the question is, given the test that we're using, the fact that the test has both a sensitivity and a specificity of 0.95, what does that imply about the significance level for the test? So again, in general, in the general hypothesis testing situations, we would be able to select the significance level that we choose to use, but in this case, the significance level is baked into the screening test itself. All right, and so again, we're using a screening test that has a sensitivity of 0.95 and a specificity of 0.95. And so the question is, what is the significance level for this test as we are thinking about this? Well, the significance level of the hypothesis test is equal to the false positive rate of the drug test, and therefore can be obtained from the specificity of the test. And so in this case, alpha is equal to 0.05. And so we're getting this from the specificity through what's called the complement rule. All right, and so this is the significance level for the test, the conditional probability that the test comes back positive given that the person does not use the drug. In other words, given that the null hypothesis is true. By the complement rule, that is 1 minus the conditional probability that the test comes back negative, given that they don't use the drug, and that conditional probability is the specificity. All right, and so since the specificity is 0.95, it turns out that the significance level for this test is 0.05. So if we recall what a type 1 error represents, in this setup, a type 1 error is concluding that a person uses the drugs when in fact they do not. All right, and the cost associated with that is that the driver gets disciplined or perhaps even fired. And so with this particular screening test that has a sensitivity of 0.95 and a specificity of 0.95, we see that the probability of this occurring, this probability of concluding that a person uses the drugs when in fact they do not, is only 5%. So that is, you can make an assessment as to whether you think that's too low or too high, but keep in mind that significance level is a result of the characteristics of the screening test itself. So let me continue on. And so here we have the scenario, all right? You are a manager at the company, and on a particular day, one of your drivers is selected for testing, and the test comes back positive. So what do? Do you fire them? The question is, do you have all the relevant information at this point that you need for making the decision? We know, presumably know the accuracy characteristics of the test, but do we have everything we need to know? Now, this is a funny little cartoon here. It kind of illustrates this concept, but this is a very real world situations with real ramifications for real people. And so we really need to think about this carefully. And so at this point, do we have enough information to make an informed decision? Again, we know the characteristics of the test. It seems to be very, highly accurate, 0.95 sensitivity and 0.95 specificity. But let's continue thinking about this. Well, we don't actually have all the information we need. You'll recall in a previous lecture video that we said that in order to interpret the results of a test, we need to know something about the prevalence of the characteristic that we're testing for in the population that we're applying the test to. We need that because we need to, in interpreting the results of a screening test, we'll need to compute either the positive predictive value or the negative predictive value. If a test were to come back positive, then we would need to compute the positive predictive value. If the test came back negative, then what we would need would be the negative predictive value. And both the positive and negative predictive values depend not only on the accuracy characteristics of the test, specifically the sensitivity and specificity, but they also depend on the prevalence of the characteristic in the population that we're testing for. Now, let's suppose, for the sake of the example here, that a relatively small proportion or percentage of the drivers at this particular company are using the drug being tested for. And in particular, let's suppose that only 5% of the drivers at the company use the drug that's being tested for. And so with that assumption, that implies then that the prevalence of the drug use at this particular company, and this particular company would constitute the population of interest, and so it's a finite population, the prevalence would be 0.05. All right, and so we now have all the ingredients we need to calculate the positive predictive value, which is, again, the conditional probability that the person does actually use the drug given that their test came back positive. So that's the relevant quantity. At this point, once we have the result of the test, the sensitivity itself is not the relevant quantity. The relevant quantity that we need in order to make an informed decision is the positive predictive value. And this is a Bayesian quantity. It's a quantity that's computed from the data itself, which is obtained through the screening test, as well as this prior information that we know or that we're assuming about the population, specifically that the prevalence of the drug use in this population is 5% or 0.05. And so the relevant quantity that we need for decision making is the positive predictive value, not just the sensitivity, not just the specificity. So we cannot base our decision just based on the fact that the test came back positive in this case. We need to incorporate the information about the prevalence in order to get the positive predictive value. And so it turns out, as you can see here, that when we do this calculation, the positive predictive value is 0.5. So what does this mean? Again, given that the person's test came back positive, the probability that they actually use the drug being tested for is only 0.5, 50%. You might as well flip a coin as a decision maker to decide whether to fire or discipline them in some manner. All right, and so that's what we're saying here. Since the PPV, the positive predictive value, is 0.5, only 0.5, if a test comes back positive, you might as well flip a coin in deciding whether or not to fire the person. So although we have a screening test that appears to be fairly accurate, because of the low prevalence of drug use in this company, the positive predictive value is not that high. You'll recall that we showed that the positive predictive value is an increasing function of the prevalence of the characteristic in the population. And for populations with low prevalence, in this case low drug use in the overall company, even if a test comes back positive, the positive predictive value is going to be somewhat low, or can be low, because of that low prevalence. And we can see that here. So there's only a 50% chance that the person actually uses drugs. So we have to then decide, is the test accurate enough in order for us to make these kinds of firing decisions based on the result of this screening test? Now, if the test had come back negative, all right, so let's suppose that we randomly select somebody, we apply or have them do the drug test, and the test comes back negative, then what can we decide based on that? Well, we would need to calculate the negative predictive value, right, which again is the conditional probability that the person does not use the drug, given that their test came back negative. So that again is that's once a test comes back negative, the quantity that we need to consider is the negative predictive value. All right, and in this case, the negative predictive value would be 0.9972. So we would be almost assured that the person does not use drugs if their test came back negative. All right, and so we can be very confident then that a person is not using the drug when their test comes back negative. But on the other hand, if their test comes back positive, we really can't be too sure about whether or not they're actually using the drug, and we would need to be very careful in making decisions in that case. Now, in reality, in a situation like this, especially in a situation where you have a population of employees where the prevalence of drug use is very low, what we're seeing here is that we would need a much more accurate test in order to have a high enough positive predictive value to be able to act when somebody's test came back positive. So in your opinion, is the drug test that's being used in this situation adequate for the situation? If not, what kind of test characteristics would you like to see? And so would we need a test that has a higher sensitivity? Would we need a test that has a higher specificity? Keep in mind that for a given test, there is an inverse relationship between the sensitivity and the specificities. So for example, if we were to make the test more sensitive, then we would necessarily be decreasing the specificity of the test. And vice versa, if we were to increase the specificity, then we would necessarily be decreasing the sensitivity of the test. And this is typically done adjusting the sensitivity and specificity, especially for something like a lab test like we're talking about, by adjusting a threshold above which would be the conclusion that the test is positive. And so you can adjust that threshold, and by doing that, you are adjusting the sensitivity and the specificity. But again, you've got this inverse relationship between the sensitivity and the specificity when you're adjusting that threshold. And so the question I have for you is that, if you consider that the test being used is not adequate, all right, and that would be, for example, because we really can't make a firm or have a confident decision when the test comes back positive. So what could we do, if anything, to the sensitivity or the specificity of the test in order to increase the positive predictive value when the test comes back positive? So that wraps up this particular application. We will look at another application of screening tests in the next lecture video.